Alright, recording is rolling. So, agenda today. Do you guys remember yesterday I did most of the textbook homework questions with you guys? There was one that I skipped because it involves some stuff that I'm going to teach you guys today. I'm going to tell you guys about rotational uh, kinematic motion. Oh, there's a quarter page I meant to hand you guys. You guys got all your papers back today, but. Oh, yeah, it's from last class. Or, hold on. No, sorry, I missed it. Um, Alright, so give you guys this quarter page that what's on this, it tells you the new rotational kinematic stuff that I'm about to give you guys, and the now what it's analogous to. So there's some new concepts that have analogous linear motion parts. I'll show you, and then what we're going to do later today is go back and hit that one textbook problem that I skipped earlier, and then we'll end class with the compute. So let's see something play out first, and then we'll see what we need to solve this. Okay. You guys see these three Roosevelts right here on this turntable? You guys see three Roosevelts on a turntable? Right. So, do you think that? What if I ask you guys this question? Which one of these Roosevelts is moving the fastest, has the greatest speed? One on the inside or one on the outside? One on the outside. If you're talking about linear speed, like if you're pointing a radar gun at it, yeah, you guys are absolutely right. Would be the outside one. But you know what? There might be a different kind of speed I could talk about. Are all these three Roosevelts making the same turns per time? Do they make one revolution in the same time interval? They do. That's a different kind of speed. It's called angular speed or angular velocity. And that is what we're interested in here. So guys, look at this quarter page. So you guys saw this? Okay. So everything on the left side is linear motion, and the right side are rotational equivalents. Now, time is still going to be time, taken away in seconds. That's the only one that's the same. Before, you used to be interested in how far something moved in meters. Now we're going to be interested in how far has something turned in radians. Actually, there's different ways you can measure how far something's turned. You could also measure how far something's turned in degrees, and you could also measure in revolutions. Like if someone's made one revolution. But radians is the best measure because I'm going to give you guys some equations later that you have to use radians to directly plug in. So, next line down, where you used to be interested in linear velocity, linear speed, like meters per second. Well, now we've got this new concept, omega. Looks like a curly W, this Greek letter omega, like radians per second. Hey, how fast is something spinning? Another way to measure this might be, you guys ever heard of RPM, revolutions per minute? Ooh, that's another way to say this. So radians per second, kind of like, well, it's a different unit, it's a concept. And since we're going down the line here, acceleration, like meters per second squared, a rate change of linear velocity. Now this might be like a car speeding up or slowing down. And recently we talked about centrifugal acceleration, that would be a linear value. Do you think that this turntable might spin faster and faster and faster? Or if I let it spin and let it go, that friction slows it down, and there could be a rate of speeding up or slowing down spinning? That's what this alpha refers to. This is alpha, radians per second squared. Okay? All right. Guys got that? Now, here, let me flash just a few notes up here. Okay. So we've got this Greek letter theta, which is going to measure angular displacement in radians. Okay. I'll tell you guys these details in a few minutes. Okay. One radian, you could also think in terms of degrees or revolutions. Come back to that. Okay. There's Greek letter omega to represent angular velocity, like radians per second. And alpha, now you guys have seen this character alpha before, but in a different context. You've seen it used to measure angles before, sometimes it is, but there's only so many letters to go around before we start recycling them. So in this context, today, it's going to refer to angular acceleration, like a rate change of angular velocity, radians per second per passing second, also called radians per second squared. So a few notes that are going to help us solve that problem that I skipped yesterday. Okay. So say we're looking at a circle. And this circle has some radius, r. Oh, what if I did this? What if I took this radial size, turned it into a string, just clipped that out, and then put it right here and start winding it around the circle? You think I'd probably make it about, maybe about that far right there. It would probably be about equal size r. You guys see that? that, the size of that wedge right there is equal to, what do you think that's equal to? One radian. That is 1 radian of that would be the size. Now you might measure that with a protractor, but that will give you some number of degrees, right? Hey, I wonder how many degrees that's equal to. We can actually figure that out. Let me take you through a process here. Since I'm starting to go around the straight, hold on to that idea. Like, I wonder how many degrees that is, because I'm about to answer that in a few minutes. What if you go all the way around the circle? Wouldn't that be the circumference of the circle? And I bet you guys already know a formula that raises the circumference to the radius. What is that called? Circumference equals 2 pi r. Wouldn't that be true? Okay. All right. Now, turns out that this formula that you guys have probably known since elementary school actually is a specific version of a more general formula that I'm going to give you right now. Because it turns out that there is a way to translate back and forth between how far something turned and how far has it moved, like distance. Like here, go back to these 3 Roosevelts. You zoom out, you guys watch them spin around. I've got one that's right near the center and then one further out, one near the outside edge. What if I ask this question, like how far have they moved? Like what distance? Well, the one near the center is like pretty much 0. It just has like 0 distance. But further out you go, see how like huge circular track could be moving a far distance. Right? Even for the same angular size, right? So it goes like this. Here's how you translate. If you want to know how far you've moved, like distance around, that's equal to how far you've turned multiplied by how far are you from the center. That's why the one that was right at the center, that had 0 distance from the center, even though the turntable was turning, it was moving 0 distance. Is that? Now this expression right here, to translate back and forth between angular displacement and linear displacement, hey, circumference equals 2 pi r. Isn't that actually a very specific version of this more general formula? Because 2 pi, guess what 2 pi refers to? 2 pi radians is the same thing as 1 revolution. It's the same thing as how many degrees? 360 degrees. So 1 trip around the circle, 1 revolution, same thing as 360 degrees, same thing as 2 pi radians. Again, been telling you guys that radians is actually the best way to measure angles, and you'll see why as we start to apply some equations. Okay? Side note here, 360 degrees, where does that come from? Did I ever tell you guys that? Seems kind of an arbitrary way to be able to circle, right? Why not 100 degrees? Why 360? So can you guys think of a cyclical number that's very close to 360? Maybe like days in a year, pretty close to? Okay. Yeah, if you go back in time too, you guys know how we use a base 10 place value system, memorize characters 0 through 9, and then just repeat those. You can make any number. Right? So back in ancient Babylonia, they were using a base 60 system, which also goes evenly into 360, which is good approximation of what a day or what a year is in terms of days. Right? So relationship there. By the way, that Babylonian base 60 system is why today we still have 60 seconds in a minute, 60 minutes in an hour. Kind of handed down through time. What if I take a rate change of this formula in terms of time? Like if I divide both sides by time. Ooh, could I get something that looks like this? Like omega? How far something's, hey, is it, or, I'm so sorry, scratch that. X over t, what is X over t? Isn't that V? Yeah, like speed, like velocity. Theta over t, that's omega. Times r. Now you have another expression. How fast is something moving linear speed, like radar gun speed, is equal to how fast the turntable is turning, multiplied by your location from the center. So, you guys want to see this again? Okay, here's 3 Roosevelts spinning around. Okay. So they all have the same omega value, same turns per time, same revolutions per minute, radians per second. That's the same. Okay. But they have different r values, right? One of them sitting at 0. So it's going to have 0 speed. See if I point a radar gun at that middle one, is it going to read 0 meters per second? Okay. Then the further out you go, the faster and faster, proportional to the radius. Do you guys think you could continue this and say that linear acceleration is equal to angular acceleration times radial distance too? That would work too, wouldn't it? Okay. Side note here, centripetal acceleration and angular acceleration are totally different concepts. So they are not the same thing at all. I've just seen students mix these up before. Centripetal acceleration is in meters per second squared. Angular acceleration is in radians per second squared. So not even the same units, like totally different concepts, right? You know what else we could do with this? Whatever. You guys remember those three kinematic equations relating like distance, speed, time, acceleration, all that stuff? Okay. Like for example, you guys remember x equals v naught t plus half at squared? You know what you can do is you can actually take each one of these rotational equivalents and substitute it into this equation and get a perfectly valid new formula in terms of rotation. So for example, it says saying how far x, now you might say, how far have you turned in radians, that could be theta as a variable, is equal to omega naught t plus 1/2 alpha t squared. Okay, so time is still time taken away, but otherwise, yeah, if you pop in the rotational equivalents, you get a perfectly valid kinematic equation for like rotation. I can do that with the other two too. I can say omega final equals omega initial plus alpha t. Well, looks like VF equals V naught plus AT. Or how about this one? Omega final squared equals omega naught squared plus 2 alpha theta. Okay. You guys see the analogous formulas that those relate to? Okay. Oh, you guys see the green poster over there? So that's the linear value, linear formulas, and here's the rotational ones, equivalents. Okay. Good so far? All right. You guys know the page of notes here because we need to relate this all to like centripetal force. Like, how about this? As you guys are watching these coins spin around on this turntable, what force is actually holding the coin to the table? Like, it's not a tension force. It's a what kind of force? It's related to the normal force. You need the normal force to have it. It's called a friction force. Isn't friction actually holding us in a circle? Like if this was an air hockey table and it had some disc just kind of hovering here, I could spin the table and this disc would just kind of sit in place. As the table moves beneath it. But yeah, friction's holding it. So let's look at a top view of that and think, how would this relate to centripetal force, all this rotational stuff? Because friction is acting as a centripetal force, right? So suppose you have this turntable, there's the center, here's the coin right at the edge, some radial distance away, I'll call it R, okay? And we're gonna give this thing a spin. Maybe some omega, hey, turns per time, there's a spin rate. Okay? Like the Earth, for example, spins one revolution every 24 hours, that's a type of omega. Okay? And this coin will have some instantaneous speed v. Okay, guys remember that? Now, there's a force on this coin. Actually, there's three forces. So do free body diagram. There's a weight down and a normal force up. Well, that's into and out of the paper. So maybe I'll say like a partial free body diagram because I'm going to ignore this. The one that I really care about is the one that you guys told me. You guys told me that there's a friction force that's pulling in it. Friction force that's acting as the centripetal force. So as this thing turns, remember how centripetal force always points to the center? And in this case, it's provided by the friction. Right? So how's this all relate? Let's go. You guys remember how from your lab, centripetal force is equal to mv squared over r? You guys figure this out empirically. Or if you like, the acceleration version, centripetal acceleration is just v squared over r. If you divide through by the mass, think Newton's second law of motion. But you know what? You guys have a new way of thinking about speed, which is this right here, right? Like omega, like turn rate, radians per second. Hey, let's take this box right here. V is equal to omega times r from before. And let's substitute that right into there and there. So it's going to look like centripetal force is m omega r quantity squared over r, or if you like the centripetal acceleration version, just omega r quantity squared over r. We'll clean this up a little bit. So that would go m omega squared r squared on r, or omega squared r squared on r. And then the r is going to partly cancel. And I got a new formula for you guys. M omega squared times r for centripetal force, or just plain omega squared r for centripetal acceleration. Yeah, remember the old ways of thinking about each of those, well, they were listed at the top. mv squared divided by r or for acceleration, just plain v squared over r. So the old ways, like up to yesterday, you guys could calculate centripetal force acceleration based on linear speed. Now you can get it based on angular speed, like how fast is something spinning. Guys, all right? All right, let's go hit that book problem from yesterday. Oops. Here's you guys. Okay, so this is number 63. Number 63. A coin is placed on a vinyl stereo record that is making 33 1/3 revolutions per minute on a turntable. Hey, a coin on a turntable. You guys have been looking at coins on turntables. 33 1/3 revolutions per minute. Hey, RPM, revolutions per minute. That's an omega value, isn't it? Ah, that's why I couldn't do this one yesterday, because I need to give you guys all that kinematic info. So, what we do? Got a coin on a turntable. So turntable, coin, give us an omega value of, well, 33.333 revolutions per minute. Now, that's not the form I like. I like it in the form of radians per second, but got that. Question is, there are 4 questions. What is the direction of the acceleration of the coin? Here, throw a coin right here. Here's the coin. You guys know that the centripetal force and therefore the acceleration is both pointed in. The force is a friction force, but right, so the answer to the first question is which direction is the centripetal acceleration? It's always towards the center of the circle. Right? Next question says, find the magnitude of that acceleration. So you know the direction is towards the center, right? The centripetal acceleration. But now find the magnitude at these locations, 5, 10, and 15 centimeters from the center. What is the centripetal acceleration? 5, 10, and 15 centimeters from the center. So maybe I need like 3 coins. Need, well, okay. Some distance from the center. Maybe I'll just draw one of them. Maybe at some radial value of, let's say 15 centimeters, something like that. Okay. So what is the centripetal acceleration? I just gave you guys a formula for that. I said centripetal acceleration is the spin rate squared times the radial location. Okay. Now, the trick is this. If you apply this formula, you have to plug in an omega value in radians per second. Okay. So that's one of the powers of measuring angles in radians. Oh, you know what? Did I ever tell you guys? I missed a little detail. Let me go back and fill in a little detail right now, right? Because there was a question I was going to answer that I forgot to. Remember, I was asking you guys, one radian. How many degrees is that equal to? You guys remember how 360 degrees is equal to 2 pi radians? So what if you divide that? What is 360 degrees divided by, what's that? Or you could go 180 over pi to do the same thing. You get about 57 degrees, 57.29, something, right? So this is approximately 57 degrees. So if you're wondering, what the heck is a radian? Well, if you think about 57 degrees, that's pretty close. Okay, so we need this in radians per second. So let's start with some dimensional analysis. I got 33 1/3 RPM, that's revolutions per minute. Okay. Open up our railroad tracks for dimensional analysis. I know that 1 revolution is equivalent to 2 pi radians, because I want radians per second. Revolution, goodbye. In minutes, every minute is 60 seconds. Thank you, ancient Babylonia. And now, hey, look at that. That's radians per second. Is that right there? Radians per second? Right. So let's go 33 1/3 revolutions per minute times 2 pi radians per rev, all divided by 60 seconds per minute. We're looking at 3.49 radians per second. So that is the same thing as 33 1/3 revolutions per minute. It's equivalent. It's just a different unit, kind of like miles versus meters or something. What is the centripetal acceleration at 5, 10, or 15 centimeters away? Well, I gave you guys this formula, omega squared r. That's straight from your notes from just a few minutes ago. No, not that page. That's this page here. Okay. Omega squared r, that's centripetal acceleration. Okay. So let's do that. So centripetal acceleration at 5 centimeters would be 3.49 radians per second. Square that, multiply by 5 centimeters. Going to get, what is 3.49 squared times 5? Okay. Looking at 60.9 centimeters per second squared, or if you like, how many meters per second squared is that? Just roll the decimal over 2 places. 100 cents in a dollar. There you go. So either one of those would work. Different units, but same idea, right? How about at 10 and 15, then, so 10 centimeters away. So 10 centimeters from the center. Keep in mind, this image right here, right? So as you get further and further from the center, looks like your angular speed stays the same, your linear speed's going up. What's happening to the centripetal acceleration? Like that would be related to the necessary friction force to hold on. So the centripetal acceleration at 10 centimeters is omega squared r. This is 3.49 radians per second being squared times 10 centimeters. See what that is. That looks like 121.8 centimeters per second squared. Or if you like, that's 1.2 something meters per second squared. And finally, what about the 10 centimeter or the 15 centimeter mark? So if you're 15 centimeters from the center, what's the centripetal acceleration at 15 centimeters? That'd be 3.49 radians per second. Square that omega value, multiply it by 15 centimeters. I'm looking at 183-ish centimeters per second squared. Or you could call that 1.83 meters per second squared. So guys, what's happened to the centripetal acceleration as you get further and further out? You guys see it's getting more and more and more? So 5, 10, 15 centimeters went less than 1 meter per second squared to a little over 1 to almost 2 meters per second squared. That's it. So next question is, what force accelerates the coin? Oh, well, you guys told me that already. You guys told me it was friction force. Okay, so we already answered part C earlier today. You guys told me it's a friction force that's acting as that centripetal force. And last question, at which point would the coin most likely break friction and fly off? The inside coin or the outside coin? Okay. So say I speed this up faster, faster, faster. Which coin is going to slip and fall off first? Show of hands. How many guys say the outside one? Let's see. Oh, it was the outside one. A little faster. Oops, not that one. But the inside one just stuck there, right? Because there's not as much force necessary to hold it in the middle. Right? Guys good? All right, ready for Kahoot? We're gonna switch the screen over. All right, we're gonna do some Kahoot. Wait, share screen 2. All right, got this. Teach. This is going to be on the inverse squared law. Well, actually, it's on gravitational force equals gmm over r squared. Most of these questions are related to the inverse square part. There are a couple of questions that say, like, what if you change the mass? How does that change? Okay, so do you guys see this poster hanging in front of the room? It says F equals gmm over r squared. Okay. So that tells you the force between two objects. We're gonna write here for the video. F equals universal gravity constant times 2 masses multiplied together divided by the distance between them squared. So you got, I know you guys can't see what I'm writing. You guys are logging on to Kahoot though, right? 2 masses separated by some distance. You guys got your phones out. You're getting on Kahoot. Right. You guys see how many guys can navigate this this formula. Okay. So there's a gravitational force between 2 masses. I'm basically just drawing that that poster that's hanging in front of the room. Okay. The one says F equals gmm over r squared. I'm just redrawing that. Force. Okay. Right. So do you guys see that as either mass increases, the overall force is going to increase? Well, what happens is the radial distance between the two increases. If you increase the distance, doesn't the force get less and less and less? That's specifically an inverse square relationship. You guys remember the story with the candle and the candlelight? Like if you back up twice as far away from the candle, you only catch a fourth of the light. Ooh, so not only is the light intensity going down, it's actually decreasing it with the squared relationship. It's called an inverse square relationship. All right, so that pin will be at the bottom of the screen if you're about to hop in. Here we go. Inverse squared law. Suppose you double the distance between two objects. How does the gravity force change? So if you double the distance, or if you like the candle example, if you double your distance from a candle, what happens to the amount of light that you catch? And I might have to stop some of these questions a little short just to make sure I beat the bell. We got exactly 5 minutes left in class. Yeah, so guys, what's 1 divided by 2 squared? Wouldn't that be 1/4? So if you backed up twice as far away from the candle, you catch a fourth of the light. Same thing with gravity. So navigate that formula. 1 divided by 2 squared, that's a factor of 1/4. Right, Kaido, Cohen, and Olivia leading the pack. What if you did exactly the opposite thing? What if you cut your distance in half? Hey, wouldn't the end result be exactly the opposite of that last question? So if you're twice as close, because what's 1/2 squared? That's 1/4. What's 1 divided by 1/4? Wouldn't it be 4 times the force? Ah, you guys are catching on. Yeah. Got Cohen, Michael, Emily, Eli, Tricia. Oh, yeah. Yeah, you guys are on a roll now.
Oh, yeah.
What if you doubled one of the masses? So if you double this mass in the numerator, right? So double this mass, what happens to the overall force? A few more seconds. If you double one of the masses, then the overall force also doubles. Yeah, double one mass, doubles the force. That is a direct relationship, isn't it? Oh, Cohen's on fire. Oh, what if you tripled each of the masses? So you triple this mass and you triple this mass. Guess what is triple times triple? You guys get that? Factor 3 times a factor 3, triple. Yep, factor 9, 9 times the gravity force. Got Cohen, Tricia, Kaden, Eli, Cheyenne. Oh, what if you quadrupled your distance? So distance times 4. So let's see, that factor of 4 would be squared. What's 1 divided by 4 squared? 1/16. Yeah, that's 1 divided by 4 squared. If you quadruple your distance. Right. Ooh, Tricia taking the top spot. What if you did exactly the opposite thing? You cut your distance into a quarter. Okay, so let's see. 1/4 squared, that would be 1/16, but that's in the denominator. So what's 1 divided by a 16th? 16, right? Doesn't the force get stronger because you're getting closer? Oh, look at you guys. Look at you guys go. Yeah. Got Tricia, Kaden, Cohen, Cheyenne, and Olivia. What if you cut the distance into a third? Well, the force better be going up because you're getting closer. What's 1 divided by a third squared? Did you guys get 9 times the force? Right? I know we got fractions within fractions going on here. All right, a few questions left. Ooh, Tricia's on fire. What if you tripled the distance between two things? Oh, isn't this just exactly the opposite of what you just saw? So if you triple this distance, r, factor of 3 squared, 9, 1/9 is 1/9. Yay. All right, 2 more questions. You guys got a calculator ready? Calculator? I'll step you guys through this anyway. Yeah, we're going to beat the bell, just barely though. Right. Suppose that on Earth you weigh 500 newtons. How much would you weigh on a planet of the exact same mass but half of Earth's radius? Like you take Earth, you just crunch it down, like compress it. So let's navigate this formula. Your mass, the Earth mass, that's the same. Universal gravity, that's the same. But aren't you effectively getting sort of closer to the thing that's gravitating? So R factor of half. Guess what's 1/2 squared? A quarter. What's 1 divided by a quarter? 4. So the weight's going up by a factor of 4. What's 4 times 500 newtons? Right? 2,000 newtons. So it goes up by a factor of 4 times the original weight of 500 gives you 2,000 newtons. All right, last question for the win. Ooh, Cohen, Tricia, Cheyenne on fire, Kaden, and Olivia. Last question for the win. suppose that you weigh 900 newtons on Earth, but now we're gonna blow up the planet to, okay, so same mass, but 3 times Earth's radius, like a giant puff planet made out of like styrofoam or something. So 3 times the radial size. What's a factor of 3 squared? 9. What's 1 over 9? So a 9. What's a ninth of the original 900 newtons? Right? Yeah. You know what this is equivalent to? Is what if you had a ladder that was so tall, it was like 2 Earth radii tall. You wish at the top of that ladder. The answer would be the same. You would weigh 1/9 of your, so 1/9 of 900 newtons. That's 100 newtons. Right, to the winner's podium with the bronze, Cheyenne. With the silver, Trisha. And the gold, Cohen. Turns up, Olivia and Kaden. Nice job, guys. You earned an awesome 3-day weekend. Have a great 3-day weekend.